So yesterday we finished up our lesson, or almost finished it up, with looking at graphs of functions, and I was asking you guys to come up with the domain intervals based on the graph. And that wasn't too bad, and frankly it was an estimate at best, because we couldn't really tell where the numbers were. So today we're going to talk about the implied domain based in the algebra. So we have to talk about things that interrupt the domain, because some of our functions have domain that goes on forever, like a line, a parabola. Their domain stretches forever, right? So any polynomial you have is going to stretch on from negative infinity to infinity for just domain. But let's talk about things that don't have that sort of shape. Without looking at the graph, there's two things you guys have to look out for today. And the first being a radical, and I'm going to kind of one-up this. I'm going to say an even radical. So what I mean by that would be a square root or a fourth root.
Just thought of that.
That is good. And then the other thing you have to watch out for today are denominators. All right, let's talk about, and you want to write this down in your notes, guys. This is kind of the basis for this next part of the notes. If you have an even radical, now think about this. You have a square root, and then you're going to have some algebra underneath here. What can you not take the square root of in math?
Oh, prime number.
I think we can do both of those. Like square root of 7. I mean, it's not pretty, but like,
-1.
can't do a -1 because what happens when you square root a -1?
Pull an eye out.
Then we have the imaginary number system pop up, and we discussed yesterday we weren't going to talk about imaginary numbers. We're just going to be real numbers today. So with that in mind, I cannot take the square root of something negative. Can you take the square root of something that's 0? Like 0.
No.
Oh?
Well, yeah, you can.
What's the square root of 0? 0. So 0 is okay. So here's the idea. What?
Never mind.
You're good? Okay. So what is underneath your even radical? This thing, this algebra, it has to be greater than or could be equal to 0. I want you to write that down in your notes, okay?
I got a question.
Yes.
So if you can take a square root of 0
Yes.
and it'd be 0,
Right.
then if you divide by 0, when it
Oh,
should be 0,
that's my next thought. And no. Can you divide by 0, right? So that's my next thought, guys. So we're going to have some algebra up here, and then you're going to have like this denominator. Let's talk about this denominator. What can you not have in the denominator of any fraction, whether it's algebraic or numeric?
I don't get
What
it,
can
though.
you not divide by?
A 0, but I don't
Yes.
get it.
So you've been told that you cannot divide by
Who came
0,
up with that
right?
rule?
Well, it's not a rule. It's just, it's,
Who made that?
okay.
No, like, see, it would just be
Yeah.
like subtracting.
No, okay. I got you. When you first learned division, the inherent concept of division to small children is they throw like M&Ms or jelly beans in front of you, right? They throw something in front of you and they say, take these 20 jelly beans and group them into 5 groups. So then you guys play around with them and you eventually figure out, like, I could break them into 5 groups of 4. So they're asking you to break them into this many groups. So if we said, take these 20 jelly beans and divide them into 0 groups,
And get rid of the junk.
you'd have to make them disappear.
So that'd be
Magician.
0.
No. It would be not possible. You
How?
cannot
Just
make them disappear.
eat 'em.
Well, okay. You can make them disappear. Jelly beans was a bad example.
But I'm saying, like, if you add anything,
But you would be violating the true nature of the number then. You're changing my 20 jelly beans to nothing.
who made that rule?
It's not a rule. It's just the universe, okay? I don't know what to tell you. Can we just accept that you cannot divide by 0? Because you are not allowed to change the nature of the number. That's the idea. Okay? He doesn't like this rule. I'm sorry. Do you want me to make something up? Pythagoras did it. There, is that what you want to hear?
Sure.
All right.
I'm gonna find them.
It's the universe,
I'm gonna
man.
change the rule.
Okay, let's look at this example. This is, I believe, on your worksheet 2. We're flipping over to worksheet 2 now. All right, class. Do we have either one of these two problems? Are we looking at an even radical right now? Or are we looking at a denominator? I think yes, one of those. Which one are you looking at?
You're in, or, hang.
There's a denominator. Very good. There's a denominator. And we just decided that the universe says our denominator cannot be equal to 0. So what I want you guys to do is set up what I call an anti-equation. It looks like an equation, but you put a line through it. Because that means this can't be 0. But you can still solve the equation like an equation. All right, y'all, this is a quadratic. Every quadratic you face today is factorable. So we could factor out an x and be left with x times x minus 6. And now that this is factored, you should be able to tell me your two, in this case, anti-solutions.
X cannot be 0.
So x, good, x cannot be 0 from right there, and x cannot be 6 from right here. So I kind of skipped around a little bit here, but those are your two anti-solutions, the two problems that you're going to encounter. X cannot be 0 and x cannot be 6. All right, here's the challenge for you today. How do you write a domain interval that says every single real number on the planet is good except for 0 and except for 6?
All real numbers besides 0.
That, if you knew how to write set notation, you could do that. Do you remember that set notation from yesterday? Like x such that all real, yeah, it's not fun. Okay. Instead, you guys are going to use interval notation. It's not that bad. This first one's going to look weird, but you'll get used to it. Do you remember how to do this? Okay, so you'd start off your interval at negative infinity, and you'd keep trucking along until you hit
0.
Now, how do you tell me 0 doesn't work? Use a parenthesis. Good. Union. 0. Because all these numbers between 0, yeah.
0 to 6.
Very good. Union. And then pick up again at 6 to infinity.
Wait.
Can we discuss this for a moment? Okay. What Daniel and I were rattling off. All my numbers from negative infinity to 0. But 0 doesn't work. So we close it with a parenthesis. We jump over 0. We pick up on the other side of 0. So like you're approaching 0 from the negative aspect of it. You skip it. And now you're going beyond 0 on the positive side. That's what's happening.
What's the
Yes.
smallest number?
There's no such thing. Yes.
Why is that? Why is the middle?
Yes.
Why is that not in brackets? Aren't those included as values?
If you put a bracket here and here, you're telling me 0 is totally okay. But it's not. So all the numbers between 0 and 6 are fine. So like 0.0001, 5.99999, 0 and 6, no. Okay. So when you're writing an interval where you have to skip over various numbers, you got to do this thing. Yes, it is a pain. It's not that bad, though. I promise you'll get used to it. All right. Number 10. Let's talk, guys. Does this have any even radicals in it? Nah. Does it have any denominators in it? And I would caution you guys, you might want to solve for y just in case something weird happens. But if you add the x over, you get y equals 4x. Does that have any denominators in it?
No.
That include x. That include x.
No.
No algebraic denominators. So since there's no inherent domain questions, that means I have no problems with my domain. How do you tell me that everything's good? You say negative infinity to positive infinity. All reals, essentially, is what you're writing down. All right, this next example. Do you have a denominator? No, you don't have a denominator of algebra. Do you have an even radical?
Yes.
Ah, and what's the rule for the even radical? The stuff underneath the radical has to be greater than or equal to 0. Remember, you can have a square root of 0, so it's okay. Now you need to break out your algebra rules. How do you solve this? Add 2 to both sides. And then, now you got to remember another rule. You divide by a -3 coefficient. What happens? Yes, the symbol reverses. So that's why we're reminding you. So now it's all my solutions are less than or equal to -2/3. I like number lines. You don't have to do the number line part though. Think about where you're shading now, guys. You're everything less than or equal to -2/3. And this time, are we all comfortable with why the -2/3 actually does work? Why I'm putting a bracket on it this time? Because if you go back to the original problem, if you guys were to plug in -2/3, what's -3 times -2/3 minus 2? It's 0. So you'd have the square root of 0. Is that an okay thing to do? Yeah. So that's the very last number in the interval that's actually going to work. So how do we write this interval? It starts at negative infinity, and it stretches until negative 2/3 with an inclusion bracket. Yes. And now to really mess with you. Well, this one's boring. Who's this? What shape is this? Quadratic, so they look like a parabola. Yeah, named a parabola. What's the domain of a parabola? Yeah, so visualizing it, I know the domain's negative infinity to infinity. Algebraically speaking, do you have a denominator or do you have a radical? No, so I don't have any problems, which means my domain is negative infinity to infinity. Oh, so this guy, Mrs. Hoffbauer, bless you, she gave us a little screenshot of what this looks like. This is a rational function. Honors Algebra 2 kids, I think, have seen something like this. You may have seen more basic looking ones. Regular Algebra 2 kids have never seen this before. We're going to have a whole unit on rational functions. You don't have to know what it looks like, but from that picture, can you guys tell that there's some definite interruptions to the domain? It's like something weird happens somewhere and somewhere else in that problem. Something weird happens, okay? Just to give you guys a little insight. This branch of the rational function goes up like this and out like this, and it approaches what's called a vertical asymptote. It has a discontinuity at the vertical asymptote, and then it picks up down here, and it creates, woo, not that. It creates what kind of looks like a parabola. It's not supposed to be weird. And then again, there's a vertical asymptote. And then it picks up again up here, and it continues on its domain for the rest of time. Whoa. So what we need to do is figure out where those problems occur. So this is based in algebra. Do you see a denominator? Me too. What can your denominator not equal? Can't be 0, because the universe says so. So guys, let's solve this. I told you today that everything that's quadratic can factor. Factor this for me. -3 and -5, okay. So you must be telling me then that x cannot be 3 and x cannot be 5. So that kind of makes sense if I look at this picture. There's a vertical asymptote at x equals 3 and at x equals 5. So this domain is like good, 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 good until it hits 3, and then it goes weird. And then after 3, good, 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 good. And then it hits 5, and then it's weird again. And then after 5, it's good. How do we write that? Parentheses. Nice.
3.
Good. Yes.
U.
Yep.
Unit.
Yes.
Parentheses.
Yes.
3.
Yep.
5.
Good.
Parentheses.
Good.
U.
Wonderful.
5.
Awesome.
Infinity.
Awesome. Whew. Like that. Just simple like that, you know? I know. That's a lot. It doesn't get any harder than that, though. Okay, so the weird-looking interval where you have to jump over a couple values is annoying to write. I know. Okay, 14, star this question. I believe there's one on your homework like this, and I think there's one on your test like this. This is a very difficult question. You really got to think about it. Because I'm going to ask you two things. Do you have a denominator? Yeah. Do you have an even radical? This is the first question we've encountered that has both. So talk to me about, what do you know about denominators? They can't be 0. Talk to me about what you know about stuff underneath the radical. Usually we'd say greater than or equal to 0. But not today. In this question, because the denominator can't be 0, that forces the whole radical to not be able to equal to 0 either. So we're going to change this symbol to just a greater than. So this is a very tricky question because it has both. So ignore the equal to component on this particular case. All right. So this we kind of already figured out. You don't have to worry about that. But here you just add the 5. So as long as your x's are greater than 5, we're good. So what does that look like? So it starts at 5, and it goes to infinity. What do you think about the kid who wasn't so careful and put a bracket on 5? He's not an idiot. He's confused. Because look what happens, guys. If you plug in a 5 into this original problem, you're going to end up with 3 times 5. So 15 over the square root of 0, which means you have 15 divided by 0, which apparently the universe explodes if that happens. So, no, you can't do that. We can't include 5 as a solution, so we're using 5 with a parenthesis. Very good. All right, moving along. Let's take a look at number 15. Do you see a denominator? Sure do. Do you see a radical this time? Nope, so we just got to worry about what makes this equal to 0, which there are 2 things because you have a quadratic. And I told you every quadratic in this lesson can factor, so let's go ahead and factor out the common term of x. Notice the x that we're factoring out doesn't disappear. You can't just have like complete solutions fall off your paper. If we were factoring out like a 2, it would be fine, but you can't just have x's disappear. So this becomes x times x minus 3. So tell me your 2 solutions that x cannot be. 0, there we go. And x can't be 3. So for your domain, you're supposed to tell me every single thing on the planet that's real, but not 0 and not 3. Who's that? Yeah.
0.
Yes. Yes.
Union.
Good.
0.
Yep.
3.
Yep.
Union.
Yep.
3.
Yep. Awesome. Beautiful. Like the interval wizard. Look at you. All right. So here's some more practice of things that Mrs. Hoffbauer and I were thinking, we should probably look at again. This is actually from yesterday's lesson. I am not worried about letter A because I know every single person on this pre-calc class is going to remember to use parentheses. Or remember I showed you how to store x? You could use that storing thing if you wanted to. I would love to look at problem B though. So first thing I'm going to do is I'm going to write what's called the skeleton of that expression. And if I were to evaluate that expression at 3a, that means I'm going to throw a 3a in for all the inputs. And my only concern is how someone goes about simplifying this. So, class, what is this first term when you simplify it? It is a 9a squared. Very good. I'm always concerned people forget to square the coefficient along with the a. This guy becomes a minus 12a, and this is still a plus 10. So that was my only concern. Did you know to square the 3? Apparently you did. So this one I am very concerned about because there's one on your test like this. So again, I'm going to write out the quadratic skeleton. And then in place of all of the inputs, we're going to place an x minus 4. Now I think you guys know what I'm worried about here.
Yep.
This.
Yes.
It's not as simple as just squaring things. We do have to think about distribution and foiling. So it's an x minus 4 times another x minus 4. I love when you guys do this part in your head. I think you can collect your like terms on that foiling question in your brain. If you feel like, no, I can't, then please don't. And if it's a test, please don't take shortcuts you're not comfortable with. So this becomes x squared. And then minus 4x in the middle will be a minus 8x plus 16. And then just watch out that you are distributing a negative 4 into there. So you have a minus 4x, but now a plus 16. And then a plus 10. And then bring it on home. We have a couple of like terms we need to collect. Got a bunch of constants here. So what do we have? X squared minus 12x. Is that plus 42? Awesome. So with those 2 algebraic evaluations, because that's really what pre-calc's all about. Like, we're not going to give you the boring baby ones anymore. We're going to give you the algebra ones. Just be careful that you're simplifying the powers properly. Oh, that's old stuff, but, you know, can't hurt. This time we're going off the graph, so they are a bit of an estimation, but I do need you guys to pay careful attention to when there's an open circle versus when there's a point or an arrow. So, let's talk about domain. Remember, domain stretches, it's all your x values, right? And we don't have a function, so you have to just look. It's from left to right. Where does your domain begin?
Oh, wait. 5.
I think it's negative. I think it's negative 3 on the left, but talk to me about, is it actually at negative 3?
No.
It's open circle. So to indicate that, I'm going to use a parenthesis. And then how far to the right is this guy stretching?
50.
Yes, it does go forever. There's a little arrow there that slowly stretches to the right forever. Range, however, this one starts here and then reads from low to high. Where does it start?
4,
A -4. Now this,
including it.
very good. And then goes up.
to infinity.
Yes, on this one side it does go up forever, so that counts. Very good. I'm not going to give you this one. I know you want this one on a test, but I'm not. Do you remember how wonderful those are? Domain and range are just, yeah, forever, all the time. Polynomials are great. All right, moving on. These are not on your paper. These are just extra practice. And we did have time to do these last hour. As I told you, we sat silently and stared at each other for 5 minutes. So instead of doing that, let's do one of these. Which one do you think is the hardest one here?
Definitely pick 5.
B and C are kind of weird. We might want to look at both. Let's look at 5B. I don't think it's on your paper. Just watch. Definitely have a radical, huh? And then we got this guy. And underneath even radicals, what's the rule? Can it be greater than or equal to 0? We don't have that denominator factor anymore, right? So this is kind of interesting, guys, because quadratics are not the same as linears, and you might be thinking like, oh, I'm just going to, add the 4 and square root both sides. And I think we might be getting into a little bit of trouble with how you guys understand how quadratics behave. If I was to graph this quadratic, not the square root part, just the quadratic itself, that's a really boring quadratic that starts at -4 here, huh? And it goes like this. Oops, not like that. So I want to know when it's greater than or equal to 0. So basically, I need to know this, where it's above the x-axis. I think you know the point at which it crosses here.
0.
The y value is 0, but how far out in the x's is it? Look at the solutions to that quadratic. Do you see what magic I just did?
Yeah. No, you're hurting my brain.
Woo! What was... Oh, I did the wrong number. That's the first problem. This is a 4. Okay. You would have done this, right? But do you see what I did to that second one?
They flipped the sign.
Uh-huh.
And made
Would
it-
you have known to do that?
Oh, no.
Yeah, me neither until I thought about it really hard.
Just now.
Yeah,
Just
because I forgot about that rule on that one. Guys, these numbers over here, those are numbers that are smaller than -2, right? Yeah, so that weird, like, did you ever wonder about that rule? Like, why do you flip signs? Why do you reverse the signs? Yeah.
Oh, I get it now.
Oh, gosh. So you're creating the negative solution. It's a little confusing, yeah. A quadratic inequality is extra particularly weird. We have a whole, like, lesson on quadratic inequalities coming up. This is just extra fun. I'm not going to give you one like this on a test, so don't panic. But I will totally give you one like 5C on a test. Let's look at that one real quick. Talk to me about the fact that we have a denominator. And what else do we have? And we have a radical. So this 2x plus 6 thing, normally I would say it has to be greater than or equal to 0 if it's a radical. But can't be 0 this time. It can only be greater than 0. So this I would solve. I would subtract the 6. And then we're going to divide by 2. Well, do we have to flip the sign this time? Yeah, the coefficient wasn't negative. So all my numbers that are greater than -3, not including -3. So the domain starts at -3 and goes to infinity. I'm having some thoughts about this question here. I think I did it wrong. Because I forgot the inherent question itself was square rooted. You guys want to have fun with this one and graph it? No?
Sure.
Yes, sure. Boop. You don't have to graph it. I'll graph it. It was square root of x squared minus 4. Was that what it was? I forgot the whole thing was squared. Square rooted, rather. Silly me. Whew. Never mind, we did it right. Now that's what the actual relation looks like. Would you be able... Yeah, would you be able to like told yourself, like, clearly the domain is negative infinity to negative 2, union 2 to infinity. I mean, I don't know if I could. That's fun. All right, let's never think about that one ever again. Moving on.
Why
Oops.
does left nostril feel like I just put that sinus stuff in there where like clear sinuses like square up?
Well, I don't know the answer to that.
It's just my left nostril.
Just your left ones? Well, now the internet knows. Hey guys, can you find the next part of the lesson, rate of change? Alright. Worksheet 2B. This is your first intro to calculus concept, but it's actually one of the easiest things we'll ever teach you that's an intro to calculus concept. The average rate of change is just slope. That's all it is. So if you know slope formula, you can determine the average rate of change between two values on any curve. So this is what's happening, guys. You're going to have, typically what we have is a non-linear function. So I'm just going to make one up, right? It's going to look like this. And your calculus teacher is going to want to know eventually what's called the instantaneous rate of change. But at first when they teach it, they're going to be like, oh, so here's x equals 1, and here's x equals 4. Again, I totally made this up. And they want to know the average rate of change between them. So they're asking you about slope of a line segment, and you're applying it to something that isn't even a linear function. So it's not going to match 100%, is it? That blue curve and that red line don't quite look the same. But what happens is if you pull those two red points closer and closer and closer together, you get something that behaves more closely related to the actual function at those 2 points. So the idea is, and we're going to do one on the table of the calculator in a minute, the closer you pull them together, the closer you get to what's called the instantaneous rate of change. For PreCalc, just to get the idea, we're going to be calculating average rate of change. Guys, this is average rate of change. And I hate to break it to you, but it is totally slope. F of whatever, that function notation, remember when your algebra teachers taught you this back in Algebra 1? And they said, you know what guys, it really just represents y. Same thing here. This is like y minus y over x minus x. Isn't that slope? Yeah, it's slope. So let's find average rate of change for, this actually is a linear function, so that's super boring, from 3 to 8. So here's what I want you to do. I want you to write out your two ordered pairs using the two x values that they are asking about. And then to find their corresponding y values, you just plug it into the function. So 3 times 3 minus 4 is 5. And then 3 times 8 minus 4 is 24 minus 4 is 20. And now we go find, instead of calling it slope, I'm going to call it average rate of change. A sub ROC. That's what I tried to write there. All right, guys, walk me through slope formula. You'd start with, so 20 minus 5 over, so 8 minus 3. Y'all, you're going to get 15 over 5, which is known as 3. Can we come back to the original problem real quick? What's the slope of that line? 3. We just found slope to be 3 twice. This is kind of a stupid question. Average rate of change of a line is just its slope. But notice the next question, not a line. So this is a quadratic. You're going to have to go through the slope process, even though it's not a line. And I don't know what the slope is right now, or the average rate of change, because I have to calculate it. So x equals 2 and x equals 4. All right, plug them in. It's Friday, so you probably want to use a calculator. I get it, but I'm not going to. I'm a trooper. All right, ready? This is 4 plus 12. That's 16 minus 10. We got a 6, right? And then plug it into 4. That's 16 plus 24. I already lost track of what I was doing. 16 plus 24 is 40. Minus 10 is 30. Oh, man. All right, average rate of change is 30 minus 6 over 4 minus 2. Better known as 24 over 2, which is 12. Now that is not the slope I thought. And it doesn't matter because you're going to calculate it anyway. So what they're asking you to look at the slope of two like endpoints when they connect on the parabola. So nothing that you guys should be able to visualize. That's the gist. Okay? You're good. What we're going to do now is explore what happens if we kind of change the way we determine the average rate of change. So this is what one of the very first things you look for in calculus is this. She's going to give you a weird looking curve, and they're going to demonstrate, well, what happens if you go from point A to B? So they connected a line segment from here to here, and talk to me about how closely related that red line segment, whoops, that red line segment is to the curved part that it's supposed to be related to. They're not quite there, especially if I draw it really bad. So they're not the same. So when I find the average rate of change and they're very spread out, it's not a really good representation of what's going on. But what if we took those 2 points, those A and B points, and we dragged them closer to each other? We'll come to that in a moment. Can we talk about this? Who's that? No, it's not Bob. It's your friend, the parabola. And they want to know if the average rate of change is greater between 0 and 1 as compared to 4 and 5. So like here's 0 and 1, huh? Think about this as being like a roller coaster. Compare that slope, average rate of change, to what happens over here between 4 and 5. Which one has a greater slope? 4 and 5. It's a way more exciting roller coaster. So on a power curve like this, where it's raised to a power, the further out in the domain you go, the more intense the slope is going to become. So the average rate of change on something like this, a quadratic behaving function, is going to change as you go along the curve. This is actually a physics concept about acceleration. Yes.
So anytime that you have a parabola,
Yes.
the further distance that you have between 2 points will always, so long as they're the same sign, right?
Well, if you're on one side of the vertex, the further out in the domain you go, the more intense the average rate of change becomes. Okay. Yes.
Always.
Yes. Well, of course there's exceptions, but on this general parabola. So the one that has the greater average rate of change is this guy for sure. Without doing any math, I'm wondering if you guys can tell me which one of these will have the greater rate of change between x equals 2 and x equals 3. What are you thinking? Yeah, the higher power is going to create a larger average rate of change. So if you think about these functions being graphed, f of x equals x is just boring. And x squared we just discovered was this guy. Totally can't draw, but you know. Does anyone remember what x to the third looks like? Okay. So if you think about this cubic, between x equals 2 and x equals 3, so like, I'm estimating here, but like here and here, versus here and here, versus here and here, again, totally estimating. The green one has a much more powerful slope going on, okay? And if you think about the math associated with that, well, yeah, because you're going to be cubing instead of squaring. So that's bigger when you have bigger numbers. Okay, so it makes sense. You don't have to always do the math. This is where I want to explore on the calculator. This is what they have you do in calculus. I want you all to take your calculator, and we're going to change a couple of settings on it. Oops, let's erase that. Get that out of there. Go to y equals, clear out whatever gibberish you have there, and replace it with the function that they want us to look at, which I believe is x squared. The other thing I'm going to have you do is we're going to play with the table settings today. Usually your table is in what we call auto mode, where it just automatically fills in like from 1, 2, 3, 4, 5, and then it just spits out numbers to you in ordered pair notation, or the table at least. This time, I want you to go to your table, and I want you to put the independent variable into ask mode. So that means it's going to leave the x's empty, and it's going to wait for you to put x's into it, and then it'll spit out the y's. Usually it's auto, but today I'd like to be in ask mode for just the independent variable. So if you go to your table, and I already have this from the previous class, but I'm going to just clear them for a minute. No, not that. Well, whatever. I'll just keep it. All right, so start typing x equals 1, and then the other one is it 1.1? for that first question? Yes. So the table will spit out the y values. It's like plugging in x equals 1, plugging in x equals 1.1. And I want to quickly find the average rate of change between these two. So the average rate of change for this first set, using that slope formula, would be 1.21 minus 1 over 1.1 minus 1. Now, there is no way, on even in my best days, would I be doing this in my brain. I do not subtract, nor I do divide decimals ever in my head. No, I screw it up every time. So I'm not gonna. Y'all, type that for me. What'd you get? Thank you. All right, we're going to do a similar style problem, except we are going to change the second x value to, what does it say, 1.01? I don't have it in front of me anymore for some reason. Thank you. All right, so that changes things, right? That changes our output. So I'm going to change colors for this. Now coming up with my average rate of change for those. Again, all my math on my calculator. Do not do these in your head. And I think you end up with, is it 2.01? You type that? And then they want you to do one more change. They want you to come back and change this to 1.001. So just every time they're changing it so that your x values are just closer and closer and closer together. So recalculating the average rate of change. 1.002 minus 1 over 1.001 minus 1. So 1 right there. All right. Can someone confirm that this is 2.001? I had a typo on my notes at one point in the recent past, and I don't know if I fixed it. Is this 2.001? None of you typed it for me? You just trusted all of that on me? Guys, that is a lot of pressure. Is this not right? That's a 1 right here. I think we're okay. All right. So guys, what happens, like what trend do you notice is happening for your average rate of change? As your points are getting closer and closer and closer together, they seem to be approaching what value? 2. And you think if we got crazy, if we went like 1.0000001, I think it'd be real stinking close to 2. And that's not even as close as we could possibly get, right? Can we all understand that there's no end to this problem, right? I could get closer and closer and closer to 1 forever and ever and ever. We're not going to do that, though. What you guys are finding right now is called the instantaneous rate of change. You're approximating the instantaneous rate of change, which is a huge, huge concept in calculus. It's one of the first things she teaches you in August, September, okay? So this is a table representation of it. You guys will be looking at algebraic representations of it when you learn about derivatives and antiderivatives shortly in the course. Pretty cool thing that you'll look at the beginning of calc. We don't get to do much calc in pre-calc because we're just trying to get you set up for calc. This is one of those like, oh, you get to see this, so I'm happy to show it to you. Okay? So my lesson's done. You guys are going to finish up your, that's not what I need. You're going to finish up the assignment. Remember how oh, and there was a weird typo on purple. So that purple sheet had a typo on that first assignment, but everything else we gave you had the right numbers. So I wrote something in a post about like doing numbers 30 and not number 37. The purple had a typo. So ignore the purple sheet. Just go off of what's on your homework checklist, please. So you guys are going to complete these 2 assignments, page 9 and page 10. 9, 10, 10, 11. And since you totally did your homework last night, that leaves you with not a lot of homework. Did you guys see that I posted PDF of the book? No, I didn't, internet. Sorry. Okay, bye.